Okay, so let's untack this really cool concept that helps us visualize forces we can't normally see. Forces are pretty fundamental, actually, to understanding, well, almost everything electrical around us. Lightning, your phone.
Definitely. They're everywhere.
Okay, so let's start right at the beginning. What are equipotential lines, exactly? When we talk about them, are we just talking about points in space that have the exact same electric potential?
That's fundamentally it, yes. Think of electric potential, maybe like electrical pressure or even height at different spots.
Okay, like pressure.
Yeah, and these lines, they just connect all the points that are at the same level, the same potential. To maybe expand on that, a little electric potential is basically the potential energy a tiny positive charge would have per unit of charge at any point in an electric field.
Ah, potential energy per charge. Got it.
So it tells you how much push or pull that little test charge would feel, or, how much energy it possesses just by being there. So connecting points with the same potential means you're marking out regions where that electrical level is identical, meaning
Right.
a charge could theoretically move along one of these lines without gaining or losing any potential energy. It's like walking along a flat contour on a hill.
Okay, that's starting to make sense.
Yeah.
And you mentioned hills. This is where the analogy comes in, right? The one from the source material.
Exactly. This is the key, I think, to making it click.
Think about those topographical maps, the ones showing mountains and valleys.
Yeah, the contour maps.
Right, where you have lines connecting all the points that are the same altitude. All points 100 meters above sea level, 500 meters, whatever.
Yeah.
This is basically the same idea, isn't it? Just for an electrical landscape instead of a physical one.
Precisely. That analogy is just so powerful. A geological map shows you the 3D shape of the land using those 2D contour lines. Equipotential lines do the same for an invisible electrical landscape. They let us mentally picture the varying electrical heights or pressures.
And just like on a topo map, if the lines are really close together.
It means it's steep, right? A big change in height over a short distance.
Okay. I see where this is going. So let's apply it. What about a common case, like a single isolated electric charge, like a proton or something?
Good example, a point charge.
What do the equipotential lines look like then?
Well, if you plot them out, they form these perfect concentric circles around that central charge.
Like ripples in a pond.
Exactly like that. But think in 3D, so they're actually concentric spheres around the charge. The lines we draw are just slices through those spheres.
Okay, spheres. And every point on one sphere or one circle on our diagram has the same potential.
Correct. But the crucial thing, tying back to the map analogy, is the spacing.
Ah, right. You mentioned that.
If you look at a diagram, those circles get much, much closer together as you get nearer to the charge in the middle.
So they're tightly packed near the charge. What does that signify again?
That tight packing tells you the electric field is getting much more intense, much stronger right there.
Like the steep part of the hill.
Precisely. A small step, a small distance means crossing a lot of lines, a big change in potential. That means a charge placed there would feel a much stronger force.
So dense lines mean strong field, spread out lines mean weaker field. That's a great visual cue.
It really is.
And there's another key rule here, right? Something the source really emphasized about electric field lines. The ones that show the direction of the force.
Yes, absolutely critical. The electric field lines are always perpendicular at right angles to the equipotential lines.
Always. No exceptions.
In electrostatics, yes, always perpendicular. This isn't just some random geometric quirk. It's deeply connected to the physics.
Okay, unpack that a bit. Why is that perpendicular thing so important?
Well, think about what work means in physics. Work is done when you exert a force over a distance in the direction of the force.
Right. Force times distance in the same direction.
Exactly. Now, the electric field lines show you the direction of the electric force. The equipotential lines are surfaces of constant potential energy. If you move a charge along an equipotential line, you are, by definition, moving perpendicular to the force, since the field lines are perpendicular to the equipotential lines.
Ah, so you're moving at a right angle to the force.
Which means the component of force in the direction you're moving is zero. So no work is done by the electric field.
Wow, okay. So moving along an equipotential line costs no energy.
Yeah.
In terms of the electric
That's
field.
correct. Your electrical potential energy doesn't change as you move along that line. It's like walking on level ground on our hill analogy, no change in gravitational potential energy.
Yeah, that's a huge insight. So if I want to shuffle a charge around without the electric field making me expend energy, I just follow an equipotential line.
That's the principle, yes.
And that must have real-world uses, right? It can't just be theoretical.
Oh, absolutely. It's fundamental in loads of areas. Think about conductors like wires or metal plates in static equilibrium.
Okay.
Their entire surface is naturally an equipotential surface. Charges can move freely along the surface without energy cost from the static field. That's part of why conductors shield things inside them from external fields.
So that's why you're safe inside a metal car during a lightning storm.
Yeah.
The outside becomes an equipotential surface.
Basically, yes. The charge stays on the outside. It's also key in designing things like particle accelerators, guiding charged particles precisely, or shielding sensitive electronics. You're finding or creating these energy-neutral paths.
That really grounds it. It's not just lines on paper. It's about controlling electrical energy.
Okay, let's switch gears slightly. What if the electric field isn't from a single point charge? What if it's uniform, like between two big parallel metal plates with opposite charges?
Right, a constant electric field. That's another classic scenario.
The source showed a picture for this too, and it looked quite different.
It does look different. In a uniform field, instead of circles, the equipotential lines are parallel, straight lines, and they're equally spaced.
Parallel and equally spaced, like lines on ruled paper.
Sort of, yeah. Or maybe think of it like the lines of latitude on a flat map projection, or the steps on a perfectly even staircase or ramp. Each line is a different constant height or potential.
And the equal spacing tells us something. It tells us the field itself is constant. The steepness, the rate of change of potential is the same everywhere in that region.
Unlike the point charge, where it got steeper near the center.
Exactly. Here, the field strength doesn't change as you move around between the plates, as long as you're not too near the edges. This uniformity is crucial for things like capacitors.
Capacitors store energy, right?
They do. And that uniform field, represented by those equally spaced equipotential lines, allows them to store energy predictably. The voltage changes linearly as you move across the gap.
And are these parallel lines also perpendicular to the field lines?
Yes, always. In this case, the electric field lines are also straight, parallel lines running from the positive plate to the negative plate, and the equipotential lines cut across them at perfect right angles. That fundamental rule holds.
Okay, so we've seen circles for point charges, parallel lines for uniform fields. We've talked about spacing, meaning field strengths, and this perpendicular rule. Let's bring it back to the listener. Why is understanding all this valuable for you? What's the big takeaway here?
I think the biggest value, honestly, is the visualization power it gives you. Equipotential lines, especially when you think about them with the electric field lines, let you build a mental 3D picture of the electric potential landscape.
Like having X-ray specs for electric forces.
Kind of. Without them, you're just dealing with invisible forces and maybe some equations. With them, you can suddenly see the terrain. You can see where the field is strong, where it's weak, where the potential is high or low, and crucially, the paths a charge could take without gaining or losing energy.
It really does feel like a shortcut. Just a few lines on a page, and suddenly you can visualize this whole invisible structure.
Exactly. It transforms it from abstract math into something you can, mentally navigate.
It gives you an intuition for how charges will behave, how energy works in these fields.
And that's how engineers and physicists actually think about these things when they design circuits or analyze fields or troubleshoot problems. It's a visual language.
It lets you predict things, understand the energy involved, without needing to actually see the field itself.
It's a remarkably powerful tool for exactly that reason: prediction and understanding through visualization.